Oh, that's okay. You know what, guys? I think it's time for a video. I am puffed out.
Me too.
We were just running around in the hot sun when I discovered we needed a lesson on how motion works,
Yeah.
right?
Yeah.
So first we're going to discuss about motion.
How we run and then we just suddenly stop.
Not just that, what is the definition of motion and a reference point?
Yeah.
Then we're going to go to distance and displacement. And finally, we're going to need some help from formulas and word problems because we're going to talk about speed, velocity, and acceleration. So, why not? Why stop? Let's get going. So, in order to measure motion, you need a reference point.
So what is reference point?
A reference point. It's an object at rest used to judge another object's motion. Motion. An object changes position with respect to a reference point. Position. The place in space that an object occupies. So let's take an example. Harini, would you do the honors? Run over there, like at that rock. Now come back, crossing this plant. You see? Harini changed her position. And how do we know that? First, her position was over there at the log. And then she changed it to over here. How do we know that? The reference point. The reference point in this case is this plant. So this plant is at rest. It does not move. But we can tell Harini is moving with respect to this plant. Okay?
If that is motion, what is speed?
Speed? We're going to do that with an example.
Don't tell me I need to run again.
No, you're not going to run.
Good.
You have to walk. Then jog. Then only run.
No.
So can you please, Harini, walk to that log over there?
Not a log. It's a tree branch.
Log.
Okay.
So right now, Harini is walking. She's walking a distance from this point to the log point, right? But she's taking the time. That's all about the time. The time. The rate at which an object moves in position. So you can stop walking now. So she took that much distance in a lot of time. Now we're going to make her jog. Go. So she's jogging the same distance, but since she's running a little bit faster, she's taking a little less time. Now you're going to run super, super fast. She's covering the same distance now, but she's taking more or less time. See, the length of the distance and how long you're taking to do the motion determines the speed. So speed is basically the rate at which an object moves from position to position.
But what does rate mean?
Rate, when you hear the word rate, it's basically time. So right now when you did that example, you, in the first time, took, let's say 5 seconds. Then in the next one, you took 4 seconds. Then finally you took 2 seconds. So the time kept decreasing and decreasing as you went faster and faster. So that determines the rate of speed. So basically the whole definition of speed is the rate at which an object moves from position to position with respect to a reference point. Woo! Now we're going to get a little bit more math.
Math and physics?
Okay, so the basic formula for speed is speed equal to distance divided by time. How you write it is, wait a minute, I can't even write here. I need some help from Mr. Whiteboard. Hey, Mr. Whiteboard, can you give some examples?
Where is Mr. Whiteboard?
Oh, thank you. Take it away.
Welcome, my friends. I am Mr. Whiteboard. And Jagan appointed me for this physics video, and I hope the rest. This is going to be so fun. Now, as I was saying, we're going to discuss speed first. Speed equal to distance divided by time. That's the formula that he said. Speed is S in this formula. Distance is D. And time is T. here. Very interesting, you know. Now, our first example, chap. Chap. What is the speed of an asteroid that moves 14,200 meters in 515 seconds? So, how do we figure this out? The unit for speed is meters per second, right? So we do this quickly and swiftly. So 14,200 meters. Meters is the distance. Divided by 515 seconds. Seconds is the time. So if we do the math, I'll give you 10 seconds to do the math. Alright, so our answer is 27.18. So that's if we round it to the significant figure. Oh, we forgot our unit meters per second. That is our answer. Now we're gonna do another example. Get out, chip! Get a chip. Now, our next example. What is the speed of a certain harini that walks 125 meters, which is the distance, in 372 seconds? Now, because we're going to do a little bit more math. 0.336. That is our answer. Meters per second. Always include the unit in the answer. Well, that's it on speed. We'll catch you later now.
Thanks, Mr. Whiteboard, but we'll meet you later.
That's right, Harney. Now, since we're done talking about speed... Nope, we're not done talking about speed. Sorry. We have to talk about average speed, instantaneous speed, and constant speed. And we're gonna need some examples. Alright, average speed. Let's say, a car. So let's say that car was going on a road trip. On the first hour, it was going this amount of distance in this. So in the first hour, it was going a totally different speed. Second hour, it was going another totally different speed. Third hour, it was going another totally different speed. Fourth hour, when it reached its destination, it was going another totally different speed. So average speed is basically the average of all those speeds. So the formula for that is total distance divided by total time. This is the part where you come, Mr. Whiteboard.
I believe Jay can send me for all helpful duties. Now we're talking about average speed. So it's the same formula. Average speed equal to total distance by total time. It's still meters per second. The unit is still meters per second. Good old trip. But now, let's do our one average speed example. Yes, an example, yes. Sure. What is the average speed for a car that drives 15,000 meters in 418 seconds? So the total distance is 15,000 and the total time is 418. So let's do the math. Time's up. 35.885 meters per second. So that is the average speed of the car.
Congratulations. We officially completed speed problems. Thank you, Mr. Whiteboard. And now we're going to talk about vectors and scalars.
But what do they mean, first of all?
Vectors and scalars are two different units. So vectors, they have to have magnitude, which is like the speed and the main information, and the direction.
Yeah.
And the the scalars, they don't include direction, but they do include the magnitude. So two vectors and scalars that we're going to be talking about in speed and motion are distance and displacement. So now we really need to talk about motion. Motion is important when you're on the go, and so is scalars and vector quantities.
But what do they mean?
We already explained that, but one scalar and vector quantity is distance. Distance is a scalar quantity, which means it doesn't need direction. So distance is the amount of ground you cover, no matter which direction you take, no matter how many curves you take. That's the amount of ground you covered in meters. But displacement is a vector quantity, which means it needs direction. So displacement, I think we need an example for this explanation.
Okay, I'm gonna run.
Wait, no. You don't need to run. You just need to walk in curvy lines.
Squiggly, squaggly, gaggly lines, right?
Fast motion. All right. So
Passed the finish line!
this is not a race, but this is a major explanation for distance and displacement differences.
Yeah.
So when Harry was walking in that curvy line until that log, then no matter how much curve she took, that was her distance, the amount of ground she covered. But displacement is basically a straight line. Like, it's how many meters from the starting point to the ending point. That's basically it. So displacement formula. There's a displacement formula, people! So it is xf minus xi, which means the final position minus initial position. So when Harney was at the log, that was her initial position. Let's just say she was 10 feet. That was her starting position, 10 feet away. Then when she came back, she went back to our 0 feet position.
Yeah.
So the final position was 0 feet. So 0 minus 10 we have to do. That's the formula. So 0 minus 10 equals negative 10 feet. That basically means you could have just walked down the straight line instead of going all the curvy place. Which was like 20 feet, I guess. Like, if you walked this way and that way, that was like 20 feet. You could have just walked in a straight line down the road, which was only 10 feet. That is the difference between distance and displacement. Summarize, while distance is the amount of ground you cover no matter how many directions you take, displacement is how many meters back to the starting point you were. So that's the scum about distance and displacement. Now we're going to need some help from Mr. Whiteboard to help us with distance and displacement. Yeah?
Welcome! Sir, Jagan was just talking about distance and displacement, right? So we're going to be doing some examples. Just say there was a number line from 1 to 8. And then a caterpillar was crossing on it. So if it crossed from 1 to 8, what was the distance? Let's actually make this 0. If it crossed from 0 to 8, what is the distance? I'll give you 5 seconds to think. Time is up! So, the distance is actually 8. 8 units. Because there is 1, 2, 3, 4, 5, 6, 7, 8. So, it's 8. But what if he gone from 0 to 8 and then came back again to 0? The distance would be 16. he went from 0 to 8, which gives 8. But then he went back from 8 to 0, which also gives another 8. So it gives 16 units. Now we're going to do this related to displacement. So, if displacement, let's just say, the same example, he went from 0 to 8. 0 to 8. What would the displacement be? And he was going east. What would the displacement be? Time's up! I said time's up. We can stop putting those dots now. Now, we have to figure this out. If it went from 0 to 8, the formula for displacement is xf minus xi, which is final position, which is 8, minus initial position, which is 0. So 8 minus 0 is 8. And so, the displacement would be 8 units east. Remember, displacement is a vector, so it needs direction. Next, what if it went from 0 to 8 and then back to 0? The initial position is 0, and then the final position is also 0 because it's ended at 0. So 0 minus 0 is 0. So 0 units east. Well, any direction because it went back. So that's the scoop on distance and displacement.
Before we go into our next topic in motion, I want to give you guys a little brain break. A riddle! Riddle time! That includes you. Everyone, try to answer this. 2 hang gliders, they left the same hill at the same time, and they went in the same speed. But then when they landed at the same time, they were in different places. Why were they in different places? Cue clock effects.
I got it. Because of the wind?
Let's just say it wasn't a windy day, but you're getting closer. You give up?
No. I'm never gonna give up. Well, okay. Okay, I give up.
It's because they went in different directions. That's our next topic. Velocity. Velocity. The great velocity. The definition of velocity is speed of an object with direction of an object. Basically, is speed with direction. Sorry, I was being too dramatic there. So, we need an example.
Okay, what
You can just walk.
to that log?
Right now, Harry is having a speed of 10 meters per second. Let's just say that. 10 meters per second. But that's not the velocity, it's the speed. Velocity is with the direction it's going. In this case, that way is the way the sun's setting, so this way must be east.
I'm done.
So her total velocity is 10 meters per second east. Just because they're going in different speeds doesn't mean they're going in different directions. That was the hint to the riddle I told you. Nice riddle, huh?
It was. There was a formula for everything, but what's the formula for velocity?
Velocity equals displacement by time. Speed is distance by time. The velocity is displacement by time. So that means velocity equals the final position minus the initial position by time. We need another example. Mr. Whiteboard!
Good.
First, I have to look into the examples. The examples, as he was saying, velocity is basically displacement by time. Velocity equal to xf minus xi, which means final position minus initial position divided by time. This is the delta symbol in Greek. It means change of, which is basically the rate. So, we'll keep this formula in mind, won't we? My faithful subjects. There. What is the average velocity for Harini traveling along a marked path from the 0.85 mark? Let's keep a note of that. To the 0.53 meter in 25.1 seconds. So, what do we have to do here? The displacement of all times, the displacement. So, the formula is, when we insert the numbers, it is 0.53 minus 0.85, which is the displacement, divided by 25.1 seconds. Ain't that lovely? And I'll give you 20 seconds to do the math. I got my answer. Minus 0.0127 meters per second. That is still the one. So velocity has meters per second as its unit. Alright? Just like speed, except with direction. Alright, we have another example. Let us see what it is. What is the average velocity of a car that travels from the 102 meter location to 12.0 meter location? In how many seconds? 15 seconds. So, this is the displacement. The final position minus the initial. Oh, I'm wrong! See, the 102 mark was the initial, but the 12 mark was the final. So, this is a little confusing, but we'll get over it with math. So I'm gonna give you 20 minutes for this one. Alright, our answer is negative 6 meters per second. Don't forget the unit. Alright, I think that was our examples, Jagan. You can take the road.
Are you going to the fun part now?
Everything's fun, right?
Yeah, but is this extra % one?
We're gonna go to the next topic as soon as we discuss another branch of velocity. Resultant velocity.
Are you actually meaning a real branch?
No. Resultant velocity. With this example, we can't really use me. Yeah. How about the treadmill, right?
Okay, I'm gonna put it extra speed.
So how about you're going 1 meters per second east, and the treadmill is going 1 meters per second west. So what is the resultant velocity? 1 minus 1, 0 meters per second. Then you cancel the east to any direction. 0 meters per second, any direction, right? So that's resultant velocity. Well, now we're gonna talk about. You see what I just did there? I speeded up. That was accelerated. And now, that is also accelerated. And when I'm walking, this is accelerating. Change in direction.
Is it time for example?
No, I didn't even explain what is our next one yet. Acceleration is the rate of change of velocity. It's a vector. Vector means it needs direction too.
Yeah.
Example time. Let's say you're walking at one velocity, which is this direction.
And then I'm gonna turn around and come, right?
No. just keep walking. Speed up. That's it. Stay there. Now come back. You can come back.
Okay, you said to stay there.
No, come back.
On the straight line.
So what Harney did was accelerating. She was first starting slow, then she ran fast. So now we're gonna need some formulas. Acceleration is basically velocity by time. But what do we mean by velocity?
Yeah.
So when we write it, it's VI or VF minus VI. That means final velocity minus initial velocity.
But
So
you
over
can't write right now. We need Mr. Whiteboard.
Well, there, we have to do acceleration. What fun. Here. So, acceleration equal to final velocity minus initial velocity by time. Right? Sure. Yes. We're going to use this formula. But acceleration is measured in meters per second squared or meters per second. Sir, they're both are the same thing, but no. What is the acceleration or hurry of a hurry who first went 12 meters per second and then went to 15 meters per second? So 15 minus 12, final minus initial, in 15 seconds or 14, let's say. Sir, this is the formula. We are following the formula. Sir, let's get on with the math. I'm going to give you 10 seconds. Time up. 0.214. Six. No, not seconds. Sorry. 0.214 meters per second squared. Now that's one problem in handy. Now another problem. Harney was running 15 meters per second. 15 meters per second east. And then she ran 12 meters per second west. East, sorry. So 12 minus 15 divided by, she took 10 seconds. So let's see if we can find that. So the answer is 0.3 meters per second squared east. Well, that's it for there on acceleration. And I hope I see you in the next slide. If not, well, have a happy learning time learning physics.
Thanks, Harney, for all those wonderful examples. Thanks, Mr. Whiteboard, for all those other wonderful examples. We finished motion.
Yay! We can do motion stuff.
So our physics video is done. So now what we're gonna do?
Maybe we can play. Stop!